Thank you. So I'm waiting for the slides to come. Okay. Good morning, everyone. I'm going to talk about profile-based indirect call promotion. I cannot move slides. So I'll start with our motivation to do this work. Then I'll describe details about transformation and heuristics involved. Then I'll proceed with results in terms of the performance, runtime, and size. And I'll conclude with possible impact on related optimization and future work. So our first motivation came from reducing misprediction rate for indirect branches. Object-oriented programs are becoming very common nowadays. And one of their defining feature, polymorphism, is implemented usually through virtual function calls, which are usually in turn implemented by indirect branch or indirect call instruction in modern processors. And another thing is that indirect calls can be also common in C or C++ programs. For example, there are more than 100 such calls in a GAP application. One note, though, is that indirect branch is more difficult to predict compared than conditional branch in hardware. And while the conditional branch requires just prediction of branch directions, usually 1 bit for taken or non-taken, with indirect target prediction, we have n possible target addresses. And when architecture is moving from 32 to 64, the need for memory space grows even larger. And here's one study done by UT Austin and Intel on Intel processor with dedicated indirect branch predictor. And the set of benchmarks are common desktop applications. So they computed misprediction number for 1,000 instructions, this abbreviation MPKI, for conditional branches as well for indirect branches. And you can see that on average, the percentage of misprediction for indirect branches is 28%. And when you compare this to the percentage of indirect branches in instruction stream, which is approximately between 8, 10, 12%, you see that for indirect branches, there are 3-4 times increase, right, in number of misprediction compared to their percentage as instructions. Another motivation came from a compiler point of view. And here is the list of common profile-based optimizations, starting with inlining, indirect call promotion, various placement optimization for code in terms of basic block functions, also optimization for data placement, and of course, extending classic optimizations with profile information. And major optimization in that regard are if conversion, partial redundancy elimination, scheduling, register allocation. And one natural question is, what is the impact, or what optimization has highest impact within those profile-based optimizations? So this question was answered by a Google study with Open64 compiler on Intel 5 years ago. So they compared their base shown in these graphics is O2, IPO, FDO, which is another name for profile-based optimization. And then they turn each into procedural and profile-based optimization one by one and measure their impact in decreasing performance. So as expected, inlining has the largest impact, nearly 18%. And indirect calls is second with about 3-4% on Spec 2000 application, which admittedly are not rich in virtual in indirect calls. Nevertheless, right, we still have this data still shows importance of indirect calls. And one last motivation, of course, is that in addition to Open64, other open source compilers like GCC and most proprietary compilers like Intel compiler, HP compilers, and others, they had implemented this transformation and profiling support several years ago. So it's really time, for us as community to add this profiling and optimizations to the LLVM and Clang. So in simple terms, indirect call promotion takes indirect call or invoke and replace it with compare instruction and a direct call to the hottest target or targets. And for performance reason, very often the direct call is inline. And by doing so, ISP reduces the overhead of indirect branch execution and related misprediction penalty. From software point of view, it really helps inlining and other global optimizations. And on top of it, it enlarges the scope of optimizations around indirect calls, particularly loop and global optimizations. So here's one example of indirect call transformation with two targets promoted. On the left side, on the left-hand side, you have a main function with indirect call through function pointer fp. And we know that this pointer can go to full bar and other direct calls. And after transforming, the code is shown on the right-hand side. And you can see that we start with iCompare, which compared the value of fp to the address of foo. And if that's true, we go and execute call to foo directly. If it's not the case, then we again compare fp with the address of bar. And if that's the case, we go and execute direct call to bar. Otherwise, we execute the original indirect call. Here are the design goal we set to ourselves at the beginning of our work. We wanted to provide a general solution as LLVM transformation path at LLVM IR, and also provide many tuning options for deployment in an LLVM-based compiler, depending on the customer requirements and typical workloads. We realized that because of a huge popularity of LLVM and Clang, it is used in many different environments, from mobile, data center, clouds, desktop. And really, we expected different customers to use this transformation with different values or thresholds. Another important thing is to define clear interfaces between interacting components to ISP so that we can proceed development in parallel. So one important interface was with indirect call profiling, and we decided to do through new type of metadata, indirect call metadata, shown on the next line. You see that it starts with identifier, then I64 number, which represents the number of times this indirect call was executed during training. And then a list of pair follows, and each pair consists of a name of the function, direct target, preceded by a number which represents the number of times this direct call was executed during training. Another important interface was with the inliner component, which we envisioned to follow immediately ISP. And the general decision and agreement based on feedback from community is to defer any inlining decisions to inliner, which of course has a complete view of the application and is assumed to make better decisions. So I briefly talk about profiling, instrumentation, part of indirect call, and this topic probably deserves a talk on its own. We record an instrument each indirect call or invoke, and during training we increment counters. So at the end we have the number of times target functions are invoked. Right now, the instrumentation is at clunk level at the very end before, during the LLVM IA cogeneration. And we extended the existing profiling architecture. So I guess many credits go to B2, Butkurt, and reviewers from Google and Apple, especially David Lee, who propose extending this infrastructure to more general value profiling. And patches are being reviewed, and some of them are upstream. And we expect this process to finish in the very near future. One interesting new development, of course, is a proposal for early inline and late instrumentation. If you're familiar, the goal is to reduce overhead of profile information and for other performance reasons. So if that happens, we need to instrument also at LLVM IA level after the early inline. So here's the same example, but in somewhat more details. So on the left side, in the bottom, it shows the actual data for this, the actual metadata for this call, showing that foo is taking 50% of the time. So we can call it has 50% frequency at that call site, and bar has approximately 42%. And the third function, other, is relatively cold. So a couple of notes on the new modified code. At the end, right, you see the new modified metadata string has been updated to contain only the unpromoted calls, just other. And because we introduce control flow, new basic blocks, we need to create branch weights metadata and with corresponding numbers based on the profile information on indirect calls. And here I'll start to explain some trade-offs which are involved in tuning these optimizations. So, for example, if the control reaches the foo, we need to overcome the overhead of one iCompare, right, and one branch. Now, if the control goes through the second promoted target bar, the overhead is doubled, 2 iCompares and 2 branches, and it's reasonable to assume that on modern processor, anything promoting 3 and more targets is probably not a good idea, because it'd be too much to be overcome compared to original indirect call. This slide is just for completeness, example of indirect invoke transformation, where only one target is promoted, and it is with frequency 100% based on profile data. Nothing special here, just you need to pay special attention to identify and handle properly the normal label and the exception label. And one simple note at the end, you see that the new metadata shows zero frequency. So this is a good reason to take this code and place it in the code text section to improve instruction cache behavior as a consequence of this transformation. So I move into related heuristics that are needed to tune this transformation. There are several independent, or if we're more ambitious, interrelated questions, and we should start with which call sites we should consider for promotion, and then when we're at a given call site, which of its targets and under what condition they should be promoted. The next question is interaction with inliner. Should we add inline hints to the promoted targets? And finally, in addition to indirect call profiling metadata, we have additional profile information in terms of the function entry counts and basic blocks counts. Should we use this information for better decisions? So I'll start with the first heuristic, call site hotness heuristic. In general, if there is no concern for size expansion, we should consider all indirect call sites for promotion, because the expansion is nearly not that much, and you are replacing indirect call with conditional branch. However, for mobile applications where Qualcomm is also concerned, right, it's good to really filter out code indirect calls. There is no point if a particular code is executed 0 times to do anything with that. Although, of course, it's subject to tuning, right? So for that purpose, experimentally, we have chosen 0.001, 1000 threshold by default, and indirect code is code if its count is less than that threshold by sum of all indirect call sites counts, which is the same as previous research on ISP. Our experimental result shows that that number, its present, doesn't matter much on spec applications, which is not the case with the second heuristic, call target hotness heuristic. So the idea is under what condition to promote the most frequent target. Now we assume that the pairs in the branch, in the indirect call metadata are ordered in descending order of their frequency. So we pick the first pair, and the current heuristic is we go ahead and promote that particular target if its frequency is 40% and above than the call site count. So we try different number, for example, 30 and 50%, and for spec, 40% is the best. Then the second question is, should we promote the second most frequent target? And it's not always winning solution, but given the current experimentation, use the same threshold, 30%, use the threshold of 30% as the best, and of course, additional condition is that the most frequent target has been already promoted. And again, we allow customer to disable promotion of second target. So the next slide is on inline hints and inline heuristic. Some of you might be familiar that Clang adds inline hint for a direct call if its profile count is greater than 30% of the most frequent call count. So we also added inline hint to the promoted target under the following condition: if its target count is greater than inline hint threshold, 1% of all indirect side counts. For our surprise, just adding inline hint initially does not help us much. Performance was well below expectation. And so then we went ahead and we just realized that within inliner, there's no much action based on inline hints. So we added a small bonus to encourage inlining such calls, and we got much better results. Now, as I said before, a sophisticated future profile-based inliner should probably take all this into account. However, one note should be that direct call coming from ISP need to overcome the certain overhead, right, by compare and conditional branch instruction. So it might make sense just to treat those direct calls coming from ISP in slightly special way. But again, this is subject to further tuning and discussion. So I'll continue with the impact on Spec 2000, 2006 benchmark, C, C++, benchmark 35 application in total. On the first column, I showed 6 benchmarks, C and C++, with substantial speed up. About 11 benchmark does not have any indirect calls with them, so of course don't do anything and there's no impact. And for the remaining one, the impact is within the noise range. So the second column represents the number of static indirect call sites which are actually considered, and the second number represents the number which are promoted. And you see that for the most indirect calls that we considered, which are above this 0.001%, most of them have first branch, first target above 40% threshold. On code side, it's very reasonable, less than 0.5%, except NAMD. And those performance measurements were done with Qualcomm Snapdragon 3.7 LLVM compiler on Qualcomm ARM A57-based devices in 64-bit mode with indirect predictor with path history. So with dedicated support for indirect branch target prediction. One note here is that we estimated, we measure effect of second branch target promotion, and it only improved EON by 4% by additionally promoting 4 second targets. So with that, I would like to know that ISP is useful transformation on its own, but it's also much more useful as enabler for additional optimizations. I talked already about beta inlining. Another interesting future optimizations we consider is function placement, which means reordering of functions based on their proximity in the call graph. And without profile information, application call graph consists of direct nodes or indirect nodes, and indirect nodes without profile information will point to every other nodes, which it's difficult to optimize and to cluster, right? However, with profiling information, we can reduce the number of outgoing edges just to the hottest targets. And this probably will help us to achieve better function ordering. And of course, this will not affect any size does not affect will keep the size the same. And another interesting application of ISP is for enhancing thin link time optimization and auto FDO. Those are two advanced link time frameworks. And ISP would help to better partition call graph so that the infrastructure will end up with better clustering. The idea is to find, generally speaking, strongly connected component on the whole call graph and to optimize only within each cluster. For future work, we plan to investigate interaction with specific hardware which is present for target processor, for example, size, size of indirect branch table, and also other microarchitectural features. So one restriction or recommendation on ARM64 software guide is not to have more than 2 branches in a specific region. I assume this is related to the finite size of branch target tables. And another interesting idea is to consider function entry profiles, counts, and basic log profile information just to derive additional heuristic to improve further performance and code size. So with that, I'd like to conclude my talk. In terms of the acknowledgement, many thanks to Betu Buutkurt, who implemented profile infrastructure, and I had a nice discussion on promotion. David Lee, who provided great feedback both on profiling infrastructure and promotion, and Teresa Johnson, who gave feedback on requirements of thin LTO. And I'm open for any questions. Thank you.
Okay, thank you, Ivan. So we have about 5 minutes for questions. We have a mic over here, if you don't mind, and I'll stand over here for the side.
Yeah, I was just wondering, you mentioned auto FDO and whether you've done any initial experiments with hardware profiling and compared it with classic programming profiling techniques.
So for auto FDO, I guess the better people to answer are the engineers from Google, right? So no, the short answer, we don't do any experiments with FDO. Yeah, okay, then Diego remind me that there is both on PGO, profile guide optimization, when we will certainly discuss this issue about FGO and other things.
We have a question over here.
Sure.
Have you thought much about how to merge value profiles that deal with indirect function calls and actual call graph and instruction level profile information in order to get a unified view of the two?
Well, I mean, the work I described is mostly in Qualcomm source tree. And since then, right, we propose indirect code profiling. And we got this good feedback, why not extend to general value profiling. So Betu is actively implementing feedback from community. And we're certainly going this way, value profiling. And based on my understanding, the only thing that this promotion transformation needed is this metadata string, and it's not going to change, right? Other than maybe just shrinking indirect code string, right? So I expect the heuristic I described to be posted right after the whole profiling infrastructure is upstream.
Okay.
Does that answer your question?
Not really. I think it'd be useful when writing the transformation to look at how to merge data in a global profile with your indirect call value profile. But
So,
if you're not there yet, then
No, I guess-
it's something for the future.
I guess in terms of the LLVM IR, after this transformation, we properly update indirect cause metadata and branch metadata, and all subsequent users of that are going to use the new modified data. But you're talking about maybe in context of thin LTO, right? No, okay. I can talk later on.
So I have two questions. First, can you talk about the overhead of the instrumentation?
So the overhead was, again, I mean, should we talk about indirect call instrumentation or value
Indirect call.
profiling instrumentation? Because this.
Yes, indirect call instrumentation.
So for that, I think B2 posted numbers on the mailing list, and it's certainly, I believe, less than 10% on Planck. Overhead in terms of compile time or the size of the profile data?
Okay, the second question is, in the experiment result, it showed the how many times you do the indirect call promotion. So I want to know how many times you do the inline after the indirect call promotion. And do you have the data for if we only do the indirect call promotion without inline?
Yes, as I mentioned in the presentation, when we just added inline hint, or even without inline hint, right, the performance was not great, right? We have maybe just Ion and Povre.
Inline is because sometimes you don't have the body to inline, right? You don't see the body. So because you don't do this is just O2 compilations, not LTO. So you don't see all the bodies, right?
No, this optimization is module pass. So it was implemented as module pass, and it is only on the LTO. So yeah,
yes,
we don't do. I guess to answer your question, yeah, we potentially can do this at O2 within the file structure, right? In the context of IPO within the file, right? But we right now all data is shown are as a module pass, and if we don't see the body, right, of the direct target function, we don't inline. Yeah.
Yeah, you don't inline, but
no, we don't promote. You don't promote.
You don't promote?
Yes, you don't promote.
Oh, okay.
I mean, it's yeah, it's conceivable we can do O2 file scope, but in our implementation, it is only on the link time, LTO, on the O3 and above.
Okay, we have time for one more question.
Great talk. Thank you for giving it. I was interested, your comparisons in the generated pieces of code were against particular function pointers. And in the case of virtual method dispatch, you're going to be getting those function pointers from vtables. And
yeah.
Ultimately, the vtables are capturing type information. And so it seems like this is kind of type profiling, or it can be used to kind of infer type profiling. And I'm wondering if there's kind of future optimization work that can kind of be built on this work.
Okay, so just to clarify situation, since we are instrumenting pretty much at the beginning of LLVM IR, both virtual calls and indirect calls, they represented LLVM IR as normal indirect calls. So we don't distinguish between virtual calls coming from virtual original source virtual function or normal indirect calls, right? Now, so there's certain optimization we can do if we somehow recognize that this call is virtual, and I can see in the code that just before this function pointer, we are accessing virtual table, so we can certainly do some further discovery of this structure to do some additional optimizations. But I hope that the main work will come from static devirtualization, right, which is somewhere higher in the clunk. So this is the vision, right? And certainly, right, there's some previous work when we profile for types. And once you have this type profile, you can certainly do something else. But just to clarify, we don't distinguish between virtual calls and indirect calls. They're the same for us.
Okay, let's thank our speaker, Ivan, one more time.
Thank you.